Dear PhD Prize Award Committee, my name is Siyuan Zhou and I have graduated from PhD program of Electronics and Telecommunication Engineering in March of this year. My supervisor is Professor Carla Fabiana Casilini. From January of this year, I was a research assistant at Politecnico, and then I left at the end of July. First of all, I would like to express my sincere gratitude to you for providing me this opportunity to present my work during my PhD career. The research that I have carried out could be categorized into these two main subjects. The first is on the physical layer analysis of multiple antenna communication systems. In particular, the mutual information of MIMO block feeding channel is studied. We first consider the scenario where neither transmitter nor receiver know channel state information. Then we consider the case where both transmitter and receiver have knowledge of imperfect channel state information. Finally, we analyze the channel capacity of MIMO relay network over relay rising channels. The second main subject of my research focuses on the network configuration of LTE broadcasting networks. Based on the 3GPP protocol, LTE broadcasting service, which is known as Enhanced Multimedia Broadcast and Multicast service, is proposed. We first presented real-time scheduling algorithms for content broadcasting. After that, we studied the optimization problem of network configuration for eMBMS in LTE networks. In this short talk, I would only focus on the first item of our contribution. Before the description of this work, I would like to first give an introduction of the MIMO block feeding channel. MIMO is an acronym standing for multiple inputs and multiple outputs. As we can see in this figure, there are two antennas equipped as the transmitter side and three antennas equipped as the receiver side. Each pair of antennas is able to communicate through the wireless channel. Compared to the traditional single antenna system, MIMO system could provide a number of benefits, including multiplexing gain and diversity gain. Multiplexing gain means the achievable data rate of the system can be increased. Diversity gain means the post-processing reliability of the system is improved. MIMO has already been encompassed in several wireless protocols, such as Wi-Fi, WiMAX, and LTE. In the forthcoming 5G wireless systems, MIMO is still believed to be an important technology. Mathematically, in MIMO systems, input signal, output signal, as well as the noise can be expressed by vectors, while the wireless channel can be represented by a matrix H. The number of rows of H represents the number of antennas at the receiver, and the number of columns of H represents the number of antennas at the transmitter. Therefore, the transmission at time k can be written as yk equals to matrix H times vector x plus n. Note that here the entries of the channel matrix are randomly distributed. If the channel entries remain constant for the B symbols, and in the next B symbols, the channel is updated to a new realization independently, the channel is called MIMO block feeding channel. For example, a 60 mph vehicle operating at 1.9 GHz has a coherence time of about 3 milliseconds. A signal with 30 kHz symbol rates has 100 symbol periods. As shown in this figure, in MIMO block feeding channel, the channel experiences an independent realization in a period of B symbols. If we consider a MIMO block feeding channel, the channel matrix H will stay constant from time t0 to time t0 plus b. Therefore, the input signals turns out to be the matrix with dimension n times b. N is the number of antennas at the transmitter sides. Now the transmission can be written as the matrix Y equals to the square root of gamma times matrix H times matrix X plus n. Gamma here represents the normalized per transmitter antenna signal-to-noise ratio. So our objective is to provide compact expressions for output statistic of MIMO block feeding channel in non-coherent setting. Non-coherent setting means no instantaneous CSI is available at transmitter or receiver. So we have utilized the finite dimension random matrix theory to derive the output density, and then we use the hybrid method, means partially analytical and partially Monte Carlo, to compute the achieved mutual information of the system. Our roadmap is first to derive the output PDF analytically, which is Py and Py given x here. Then we use the results of the output PDF to compute the entropy of the output numerically, which is Hy and Hy given x here. After that, the mutual information I of the system can be obtained. Finally, we compare our results of the mutual information with the given approximation results. These are the numerical results of the mutual information. The dots represent our results and the lines represent the approximation results. In the left figure, we increase the number of antennas at the receiver side while keeping the number of transmitter antennas and the block length fixed. In the right figure, we increase the number of antennas at the transmitter side by keeping the number of receiver antennas and the block length fixed. In both figures, our results match well with the approximation results, which means our results can be verified. Now we reach the conclusions. We have studied the MIMO block fitting channels in non-coherent case by using random matrix theory, and we first can provide a closed form output PDF, and second, we use the output PDF to numerically evaluate the mutual information of the system. And this work has been published in the IEEE Transaction on Information Theory. And this list represents some of my publications during my PhD periods. And this is the end of the talk. Thank you very much.